Welcome to Geosetta, a web-based application built to host historic geotechnical data. Geosetta is a non-profit Maryland-based company. The name gets its inspiration from the concept of a Rosetta Stone that unlocks access to the tremendous amount of available historic geotechnical data. Geosetta serves two main functions. It provides a platform for hosting subsurface investigation data from various publicly funded sources throughout the United States. It also provides a preliminary understanding of anticipated subsurface conditions at any project sites, thus assisting in the design of a cost-effective and efficient subsurface exploration program. This is possible because Geosetta has developed geospatial and visualization tools with machine learning techniques applied. Basically, it provides geography and mapping of any selected project site in the country with GPS and GIS precision, as well as geotechnical tools that would allow visualization of existing and/or anticipated subsurface conditions thanks to the machine learning part. While it offers insight, Geosetta is not a substitute for site-specific subsurface investigation. Geosetta's mission is to build a repository of subsurface investigation data from publicly funded sources and derive from that data valuable geotechnical engineering tools for the mutual benefits of the data owners and the geotechnical and civil engineering profession. Geosetta is partnering with and contributing to the development of GeoInstitute's data interchange for geotechnical and geoenvironmental specialists DIGS to provide a user-friendly interface to view the data. How does Geosetta work? The Geosetta application is a geospatial mapping system leveraging machine learning methods and point cloud visualization tools. The images here show the online portal MapView, which displays the available historic data in aggregated data bubbles. When you zoom in a location or search for a specific location, you are able to see individual data points. By clicking any historic data point or a selected specific point location, you are offered a menu from which you can view the historic boring data as a DIGS file, which you can download as is or as a PDF log. You can also generate three-dimensional point clouds of your site or open the USDA soil survey map of your location. One of Geosetta's features is the DIGS file viewer. Geosetta automatically extracts GINT or DIGS datasets into its GIS database and generates DIGS files on demand. It provides an HTML viewer for DIGS boring logs, which allows for instant viewing on any device with no proprietary software required. On the right side, we have an example DIGS file download, currently simplified to show the boring location, elevation, soil stratigraphy, groundwater level, and measured blow counts. The plan is to enhance the viewer to include laboratory testing data and other in-situ testing data as well. Geosetta's machine learning. Geosetta developed machine learning methods to train deep neural networks and reinforcement learning of historic drilling data. Example, data sources is auger boring, standard penetration testing, and foundation installation. Example data inputs from these sources are soil strength, groundwater level, depth to rock, soil and rock classification, as well as rock quality. The primary machine learning method used in Geosetta is the supervised learning algorithm, which consists of a target outcome variable to be predicted from a given set of independent variables such as those listed in the previous slide. Using these variables, a function is generated that map inputs into desired output, and therefore we will be doing continuous training until the model achieves the desired level of accuracy and be ready to do predictions. There are a couple of modules in this method, but the module that is used by Geosetta is the tabular data neural network model, such as FastAI or random forests. it delivers outputs such as predicted SPT data, soil types, strength, rock depth, water depth, but it can also be trained to provide pavement thickness predictions. Here's an example showing predictions using machine learning. These 3D graphs show the actual versus predicted grain size distribution of a particular soil profile. Here the clay is represented in red, sand in yellow, silt in brown, and gravel in black. As you can see from the distribution of the soil types between the actual data and the model prediction, we can see a pretty good match between the two. Sample output from the model is displayed here to the right, and it shows the predicted soil type or soil grain size in depth, including refusal based on the blow counts, as well as predicted SPT and range, also distributed in depth. This can be plotted in terms of blow count versus depth. And what's nice is that the model or the program will calculate a grain size confidence at any depth. In here, for example, we're showing the grain size confidence at 4 feet, indicating that there's a 40% confidence that the soil would be sand, and about 32% that it'd be silt, and less of that it's clay. So this prediction indicates that we have or likely have a silty sand at a depth of 4 feet at this point. This is a brief description of the process of training the neural network. So step 1 is to collect historic data. Step 2 is to extract meaningful variable from this data, namely the location, northing and easting, elevation, SPT and values, infiltration data, and grain size distribution data. Then in step 3, repetitively process these variables through a neural network to produce desired outputs, the dependent variables, to reach a satisfactory accuracy, and from that build tools that utilize the calculated numerical models to produce predictions such as the 3D soil distribution graph example that we showed in the previous slide. Now, some visualization tools offered by the application. Geosetta developed a pipeline to automatically generate point clouds from state digital elevation data and satellite imagery, combining it with machine learning to produce point clouds that include topography, site features from satellite imagery, but also subsurface condition predictions used the machine learning component. So in here we're showing an example point cloud of a particular site that will show, in addition to site features, topography, elevation, the predictions in terms of blow counts. So in here we see low blow counts in the red, changing into higher blow counts in green, but depth to bedrock in gray color.